Hello, welcome to a guide to custom hardware development using dynamic PL reload within AMD's embedded development framework. This how-to video is based on and compatible with the Embedded Common Platform Configurable Example Design (CED), which is the Vivado design used to create the EDF BSPs, the EDF pre-built OSPI firmware, and EDF Linux disk images. The video will begin by accessing and compiling an EDF-compatible Vivado base project targeting the VEK385 board. This base design can be found in the AMD Hardware Platform GitHub repository. Next, a child project will be created based on this base project, and the Knox solution file from the base project will be extracted and imported into the child design so that an identical NOC configuration will be used to ensure compatibility. A new custom IP will then be added to the block design so that the PL is modified, allowing LED control to come from the DIP switches. The child project will then be built, and the design compatibility will be compared to the base project. After the compatibility is verified, an XSA will be generated. The system device tree will then be extracted from the XSA using SDT-Gen utility, and a PL firmware bundle will be created. Last, the firmware bundle will be copied to the running VEK385 board running EDF Linux, and the new PL will be loaded and tested to ensure it is functioning properly. The custom hardware development flow, or the Vivado CED flow, starts with creating the new Vivado design based on the base design, which is the Embedded Common Platform Configurable Example Design. This new child project is then modified and/or extended by adding new RTL blocks, or IPs, as per the requirement. Dynamic PL reload, using segmented configuration, is used to implement application-specific incremental hardware design updates within the EDF framework. Segmented configuration refers to booting the PS first and deferring the PL firmware to boost the Linux boot time. The deferred PL firmware allows the programmable logic to be reconfigured while maintaining the existing processor system and NOC configuration. The base hardware design is sourced from the Embedded Common Platform Configurable Example Design (CED) and is integrated in the boot firmware and Linux image. The processor system and NOC defined in the base hardware design remain unchanged to ensure compatibility when loading the new PLPDI. A modified child hardware design is created to implement new PL logic. This results in a PL-specific firmware bundle containing only the PLPDI and device tree overlay. This firmware is loaded at Linux runtime via DFX Manager client. Consistency between the base hardware design and the child configuration is maintained by importing the Knox solution from the Golden project and validating compatibility using PR Verify. Once the new updated child hardware design is ready, it is implemented to generate XSA. The system device tree is extracted from the XSA, and a PL firmware bundle is created, which is then deployed back to the running VEK385 board running EDF Linux, and the new PL will be loaded and tested to ensure it is functioning properly. This approach enables custom hardware development without regenerating the base system image or modifying the EDF platform. Only the PL domain is updated. First, let's look at an overview of how PL reload for segmented configuration works. The segmented configuration approach enables users to delay delivery of the PLPDI image. Moreover, users can dynamically reload the configuration of the PL on the fly, changing the functionality of the design in the PL domain. This effectively provides a simplified entry point to a dynamic function exchange DFX-like solution without requiring the use of a full DFX design flow within the Vivado design suite. However, it is important to establish consistency between multiple runs so that the NOC usage and interfaces match. To ensure consistency between implementation runs and their corresponding PDI images, the NOC solution is locked and then can be exported from one run and imported into another. The recommended approach to establish consistency from one project to the next is to create a golden project and spawn all new variations from this source. This ensures the same processing system, PS domain consistency, from the top-level block design name to NOC IP configuration and NOC connectivity. If designers expect to modify the NOC usage within the PL domain, either entirely in the PL domain or the PL NMUs connecting to the PS NSUs, it is advised to separate this dynamic portion of the NOC into one or more unique NOC IP instances. This allows the PS NOC to more easily remain untouched from one run or project to the next. When a design is complete and is routed, first, lock all the NOC path segments that are tagged with the initial boot property, as well as all the segments connecting the PS domain to the PL. Then, export the NOC solution from a routed design checkpoint and write it as an NCR file using the write NOC solution command. To replicate the NOC solution, read in the NCR file by setting the NOC solution file option within the implementation run properties. This option calls the read NOC solution tickle command prior to running place design to apply the NOC solution from the initial run. When the second design image is completely implemented, run the PR verify command, which will confirm that the NOC solutions are identical and the PL images can be interchanged. This must be done directly in the Tickle console to identify the two routed checkpoints to compare. To follow along, ensure that Vivado is installed on your machine. This video will be using Vivado 2025.1 on a Linux machine. A VEK 385 board running EDF Linux will also be needed. For assistance, booting a VEK 385 using the EDF Linux, BSP disk image, and OSPI boot firmware, please refer to the Getting Started with AMD Embedded Development Framework EDF using pre-built images video. Let's begin the demo by compiling the base CED project. The CEDs can be found on the AMD GitHub in the AMD Yocto HW Platforms repository. Note that if you are using the Vitis extensible platform and the default PL payloads, there's no need to recompile since the base NOC solution file .ncr file is shipped with Vivado. Clone this GitHub repository with the branch for Vivado 2025.1 into your working Linux directory. Next, navigate into VEK 385 base directory. Here, a makefile along with helper scripts exists to assist in the compilation of the CED project. Before running, the environment must be sourced with the Vivado version that the CED is from. To do this, run source, then the path to your Vivado installation. Now the project can be compiled. To do so, run make xsa. Once the process is finished, open the Vivado project. After root design and implementation, the NOC solution file was automatically created. To see its directory, look at the implementation properties as shown here. Take note of this directory since it will be needed in the child project. Let's create a child project based on the CED base project so that an IP can be created and added to the design to showcase the full dynamic PL reload functionality. In the Vivado GUI, navigate to File, Project, Save As. Enter a name and specify the location you wish to store the project. Open the new project if it does not open automatically. Navigate to the Tickle console and run the set property command as shown here and specify the path for the NOC solution file from the base project to import the NOC configuration data to this new project. This is necessary to ensure consistency between implementation runs and their corresponding PDI images. Now that the Knox solution file is imported, the design can be modified. In the current design, the LEDs are being directly controlled by software through the AXI interface. A new PL payload will now be added by creating a new IP block to allow the LEDs to be controlled by the DIP switches on the VEK 385 instead. It is important that the PS and Knox settings aren't edited, since this may break compatibility with the pre-built bootpoint DI and/or the pre-built EDF images, which are based on the EDF specifications. If PS settings are edited, this moves into a full custom flow, requiring regeneration of the EDF Linux image and update of the boot.pdi. Now create a custom new IP and add it to modify the existing PL. To do so, create a new project for the VK385. You can change the name and save location, but this project will just be used for IP creation, so they are not important. Once the new project opens, add a design source titled DIP Control. In the module, allow for the input of the DIP switch to drive the output of the LEDs as seen. Note that this is just an example of how you can add an IP. Feel free to use your own custom module or PL modifications. To create and package the IP, go to Tools, Create and Package IP. Package the current project and include a repo directory of your choice. In the new interface, go to Ports and Interfaces to create custom interfaces that are compatible with the peripheral GPIO pins in the base project. First, create a master pin for the LED output. Select the compatible interface domain GPIO RTL under the I/O interfaces. In the Port Mapping tab, connect the tri-state output signal to the tri-state output for LED. Now repeat this process for the DIP input in monitor mode. Set the interface to GPIO RTL and map the tri-state input port to the DIP tri-state input port in the port mapping. To finalize the IP, go to Review and package the IP. This will add it to your IP catalog. Back in the child project, the IP repository that the new IP was saved in must be added so that it can be accessed. Navigate to the Settings, IP, Repository, and add the directory. The IP can now be added. Open the block design and find the GPIO LED and GPIO DIP external interface pins on the right-hand side. Enlarge the area. Remove the connection between the AXI GPIO 0 blocks GPIO port and the GPIO LED external interface. Right-click blank space and select Add IP. Search for the DIP control IP that was created. Connect the created DIP control block's LED port to the GPIO LED external interface. Next, connect the DIP port on the DIP control block to the connection from AXI GPIO 2 block and GPIO DIP external interface. Last, connect the clock and reset pins to the AXI clock and reset connections into the other AXI interfaces. Once everything is connected, the PL edition is now complete and the design can be compiled. Run synthesis, implementation, and generate the device image for the design. This will all happen sequentially when selecting Generate Device Image. Once the design runs are all complete and the device image has been generated, the validity and design compatibility can now be tested using the shown command. It compares the NOC routing that was captured in design checkpoint files during design generation. To do this, navigate to the Tcl console in the Vivado GUI and compare the routed DCP designs from both projects. Run the shown command with initial option, pointing to the base design routed DCP and the additional option pointing to the child design routed DCP as shown here. After PR Verify finishes its run and it shows no errors, the firmware bundle from the child project can now be generated. First, the XSA must be exported from the Vivado project with the Include Bitstream option enabled and save this to the location that can be easily accessed. Next, leave the Vivado GUI and navigate back to the directory where the project resides in the command line. First, extract the system device tree from the exported hardware, XSA, from the Vivado child project. This can be done using the SDTGen utility. To use this tool, Vivado must be sourced in the directory if it is not already. Next, to get into the SDTGen interface, run SDTGen. Specific SDT parameters can now be entered to configure the device tree generated. Set DT param directory, mysdt, creates a directory in which your system device tree will be saved. Set DT param board DTS, which defines the target board that will be used. The target board used here is the VEK 385. Set DT param XSA that will attach your Vivado project hardware to the system device tree. To make sure there is a proper handoff between device trees, run set DT param Zocal enable. To generate the system device tree, run generate SDT. Once complete, the system device tree is now generated and stored in the mysdt directory. To leave the SDT environment, type exit. Let's now create the firmware bundle of the generated SDT to enable DFX Manager client to manage multiple PL payloads and configure the PL from Linux. The firmware bundle is a directory containing a device tree overlay.dtbo, PL payload.pdi, and .json file DFX Manager client configuration file. Create a directory to contain the files in the firmware bundle and copy in the source, pld.pdi file. Next, create a shell.json file in the firmware bundle directory. To do this, run the shown command. Add the shell type as xrtflat and num slots as one wrapped within curly brackets. Next, use lopper to create the Linux device tree from the system device tree. To do this, run the lopper command, as shown here by giving the paths to the SDT and overlay files. Last, use device tree compiler to create the device tree overlay.ttbo file. To do this, run the shown command. You now have a firmware bundle directory that can be transferred to the running system for use. Copy this firmware bundle to the VEK 385 board's home directory that is running EDF Linux. Once the new directory is copied to the board, it must be moved into the proper location so that it can be treated as a firmware bundle. The easiest way to do this is to copy the directory with the super user privileges and the -R flag for recursive copy to the Xilinx directory. To confirm that the firmware bundle was added successfully, run sudo dfx manager client list package to see the available packages listed out. In here, the bundle from the EDFCED design as well as the newly added child project exist. To load the firmware bundle, run sudo dfx manager client load child firmware. You should see that the bundle was successfully loaded and is now running on the board. To confirm, try adjusting the DIP switch positions on SW7 and see the resulting output on the 4 LEDs. In this video, we displayed compiling and exporting the Nox solution file of an EDF-compatible embedded common platform Vivado base project targeting the VEK 385. Then, a child project was created based on the base project and a new IP was added to the block design to modify the PL, allowing LED control to come from the DIP switches. The child project was then compiled and the design compatibility was compared to the base project. Checkpoints were then verified between the base and child project using PR Verify and an XSA was generated. The system device tree was then extracted from the XSA using SDT-Gen utility, and a PL firmware bundle was created. Last, the firmware bundle was copied to the VEK385 board running EDF Linux, and the new PL was loaded and tested to ensure it was functioning properly.